Hello everybody. Today we have our last review topics from Math 1040. And these are sections 3.5 and 3.6. This is implicit differentiation and logarithmic differentiation. Now, implicit differentiation is necessary for some functions which aren't technically functions at all. I may have a function where y is implicitly defined as one or more functions of x. So a standard simple example of this is just the unit circle. This is an implicit function involving x and y, and the reason it is implicit is because y cannot be given as an explicit function of x. What I mean by that is if I try to solve for y here, I'll have y squared equals 1 minus x squared. And I can try to get y by itself by taking the square root of both sides. But what happens when I do that is I have a positive and a negative version. The problem here is that given an x value, I do not have uniquely determined y values, so this isn't a function. But the circle is still a coherent curve, and I can do calculus on it. I can find, the derivative of a part, meaning I can find the instantaneous rate of change or the slope of a tangent line to a part of the circle. And I want to be able to do that even though I cannot write the circle itself as a function of a single variable. I have to split it into a top half and a bottom half like that. So let's say I wanted to do some calculus on the circle, and I wanted to find the slope of a tangent line to a point of the circle. And there's lots of physical reasons to want to do something like this. So let's say it's find dy dx, funny line at the point, what's a good point on the circle? Root 3 over 2 and 1/2. And we want to find this derivative for the circle x squared plus y squared equals 1. This is my unit circle, so that point is on the unit circle, so I'm not doing anything too crazy. So what I do for this is I start off with my function, or my equation I should say. X squared plus y squared is equal to 1. And I want to take the derivative with respect to x of everything in this function. And I do this term by term. So I have an x squared, that becomes 2x. Plus, the 2y becomes 2y. But because I'm dealing with implicit functions here, I'm still assuming that y is some kind of a function of x, even if it's not properly a function passing the vertical line test and all of that. So anytime I take the derivative of something involving a y, I'm going to tack on an extra dy dx from the chain rule. Because I'm still assuming that y is going to be a function of x. The derivative of 1 is just 0. So after my derivative step, I'll go ahead and number these steps. We take the derivative. 2, we want to expand everything. I don't necessarily need to expand anything for this problem. And after I expand everything, I want to solve for dy dx, and that's going to involve 2 steps. 1, I need to get all the dy dx's on one side, and then I want to factor and divide. And we're going to do all these things for this problem. So I've already taken the derivative. I don't need to expand anything because my derivative ended up being fairly simple. I want to collect like terms, and what I mean, I want to collect all of my dy dx's on one side with all the extra junk on the opposite side. So I'm going to have 2y dy dx equals negative 2x. And then I want to factor and divide. And again, I don't need to factor because my function was simple. X equals negative 2x divided by 2y. And of course the 2's can cancel, so my dy dx, the slope of my tangent line given a point, is going to be negative x divided by y. So for this problem, I wanted to find out dy dx in the domain restriction of the point root 3 over 2 and 1/2. So I'm just going to plug that point into my function, or into my derivative rather. dy dx root 3 over 2 comma 1/2 is going to be equal to my x values are root 3 over 2, my y values are 1/2, leaving me with negative square root of 3. And that would be the slope at the point root 3 over 2 comma 1/2 on the unit circle. For a more involving example, I may ask you for the derivative from a function like sine of x plus y is equal to x times y minus y squared. I'm going to start off the same. I'm going to take the derivative of both sides. The derivative of sine is cosine, so I'm going to have cosine of x plus y times, from the chain rule, 1 plus a dy dx. And on the other side, I have a product rule here, so I'll have 1 times y plus x times dy dx minus 2y dy dx. Now I need to expand this and then collect all my like terms together. So I'll have cosine of x plus y times 1 plus cosine of x plus y dy dx. And over here, I've just got y plus x dy dx minus 2y dy dx. And now I'm going to collect all of my dy dx terms on one side, and the other junk on the other side. So I'll be left with cosine of x plus y on the left minus y equals an x dy dx minus a 2y dy dx minus a cosine of x plus y dy dx. And now I'll be able to do my factor and divide step. On the left, I now have dy over dx times the quantity x minus 2y minus cosine of x plus y. And I can divide, leaving me with dy over dx equal to cosine of x plus y minus y all over x minus 2y minus cosine of x plus y. I may ask for a second derivative, and to save time I won't ask for the second derivative of this particular problem. I'll do this one on the circle. I won't ask you for y double prime or d squared y over dx squared if x squared plus y squared is equal to 1. Now what we do for that is we go ahead and find the first derivative every time. Now I've already done this work, so I get to say that dy dx is equal to negative x divided by y. And what I do when I want to find the second derivative is I take the derivative of both sides again, leaving me on the left side my d squared y over dx squared, and on the right hand side I have to deal with the quotient rule. Quotient rule is derivative of the top first, so I'll simplify this. I'll call this negative x divided by y. So when I take the derivative of the top, I have negative 1 times y minus derivative of the bottom, y prime times negative x divided by y squared. You notice this time I wrote a y prime instead of a dy dx. And that's because I'm allowed to use y prime equal to dy over dx. Both of them are acceptable notations when doing these problems. I tend to avoid the y prime notation if I'm in a rush because I'm more likely to make a mistake in my work if I forget to write a y prime, for example. So if I had done this problem up here with, I'd have a cosine of x plus y times 1 plus y prime, for example. But if I'm going too fast, I feel like I'm more likely to forget to add the y prime or to write the prime on the y prime, leading to mistakes. So down here we have our derivative, negative y plus xy prime over y squared. And what I do for this is I substitute y prime back in. So I have minus y plus x. My y prime is negative x over y. Negative x over y. All over y squared. And it would be perfectly fine to just leave it like this. But if you're curious, this comes out to look like negative y squared plus x squared divided by y cubed. A consequence of having implicit differentiation allows us to deal with some more interesting derivatives, particularly those of inverse functions. So first up, I want to ask for the derivative of the natural log. Now I could technically pull this off with the chain rule, kind of like how the book does with a to the power of x. But it's helpful for us to do it with implicit differentiation, particularly when we get to the inverse trig functions. So if y is equal to the natural log of x, then an equivalent way of writing this is, that means e to the power of y is equal to x. This is either using the definition of the log notation or applying, raising both sides as a power of e. And the advantage of this is I know the derivative of e to the x, so I'll take the d dx of this new equation. Derivative of e to the y is e to the y times a y prime from the chain rule equals 1, which means my y prime is equal to 1 over e to the power of y. But since y is equal to the natural log of x, or rather e to the y is equal to x, this is just 1 over x. So the derivative of the natural log of x is equal to 1 over x. And similarly, through the same process, the derivative of the log base b of x is equal to 1 over x times the natural log of b. Now I'm actually going to use this exact same technique to find out the derivatives of the inverse trig functions. So I want to find y prime if y is equal to arcsine of x. Or, if I like to use some terrible old notation, sine inverse of x. This is the inverse function to the sine function, which is not the same thing as 1 divided by the sine function. So, this means that if I apply sine to both sides, I have sine of y is equal to x. And I know this derivative, so I'll do it. d dx of sine of y is going to be cosine of y dy over dx equals 1, which means my dy over dx is equal to 1 over cosine of y. Now I did this without saying anything on the log problem, but since I was given a problem with a function of x, I should give an answer with a function of x. So the problem is, how do I get x's back out of this cosine of y? And the answer to that is, we're going to draw a triangle. Now, this sine of y equal to x means I have an angle which is y, and sine of y is equal to the opposite over the hypotenuse, which is equal to x, divided by 1. So the opposite is x, the hypotenuse is 1. From the Pythagorean theorem, my third side is 1 minus x squared. And so my cosine of y, which is adjacent over hypotenuse, will be the square root of 1 minus x squared all over 1. So instead, my derivative here is 1 over the square root of 1 minus x squared. I'll be honest with you guys, I don't know any of the inverse trig derivatives, but I do know how to do this. So anytime I'm faced with trying to find the derivative of, inverse secant or something, I'm just going to do this process with the triangle to find out what it is. For our convenience, so we can favorite and forget, I'm going to go ahead and make a chart of all these derivatives, similar to how I did for the trig. So I'll have f of x, and I'll have f prime of x. So I prefer the arc notation, but I'm going to go ahead and use the inverse notation. If I have sine inverse of x, my derivative, as we found, is 1 over the square root of 1 minus x squared. If I have cosine inverse of x, this is the negative of 1 over the square root of 1 minus x squared. Tangent inverse will give us 1 over 1 plus x squared. This is one that I actually do remember because we use it a lot, especially in calculus 2. Secant inverse will give me 1 over x times the square root of x squared minus 1. And cosecant inverse, will give me the negative of that. Negative 1 over x times the square root of x squared minus 1. You notice a pattern developing. Anytime I have a co-version of one of my trig functions, I end up having the negative of the original derivative. So you can guess what's going to happen for my cotangent inverse. I get negative 1 over 1 plus x squared. So if you're able, you can memorize 3 of these and just remember that the version that starts with a c is going to be negative. Now something valuable that we can get from now that we have the derivative of the logarithm is the technique of logarithmic differentiation. So we have rules for, we have a power rule, which is a variable to a constant power. We have an exponential rule, which is a constant raised to a variable power. But what we don't have is a rule for a variable raised to a variable power. So suppose I had a function y equals x squared minus 1 raised to the power of e to the x. And I want to find y prime. Well, since I don't have a rule for functions raised to the power of functions, I'm going to have to try to simplify this with logarithms. And really, whenever we have exponents that we don't like, we generally take the logarithm somehow to get rid of the exponent. So I'll do the natural log of y. This is equal to the natural log x squared minus 1 to the power of e to the x. And by log properties, this means the natural log of y is equal to e to the x times the natural log of x squared minus 1. Powers on the inside come out as coefficients on the outside. And this I can take a derivative of easily now, because the derivative of the natural log of y, that's going to be, it was 1 over y times a y prime. Over here we have a product. The derivative of e to the x is e to the x times the not derivative of natural log of x squared minus 1 plus e to the x times the derivative of x squared minus 1, which would be 1 over x squared minus 1 multiplied by, from the chain rule, a 2x. Now, similar to before, since I provided a question that was a function of x, we should give an answer which is a function of x. So when I have this extra y here after solving for my y prime, I want to substitute it back for the original problem, which was x squared minus 1 to the power of e to the x. So y prime equals x squared minus 1 to the power of e to the x, adds parentheses, e to the x, natural log of x squared minus 1, plus, I can simplify this a little bit more, 2x e to the x over x squared minus 1. So those are possible now. But that's not the only thing that logarithmic differentiation has done for me. I can also simplify some of my nasty 3.2 problems. And for this I have, suppose y is equal to x squared times tangent of x multiplied by 4x minus 3, all divided by e to the x times x minus 6. And naturally I want to find y prime. Of course, you could look at this and say, hey, I have a quotient, and inside of that quotient I have a product rule. But then you think about how much are you going to have to write out for that quotient rule and all of those product rules. It's going to be rather painful and definitely would not fit on this space. But we're doing math, and mathematicians are lazy, so naturally we found an easier way to do this. We use logarithmic differentiation, because one of the properties of logs is products on the inside of a log turns into addition on the outside of a log. So instead of having to write out a whole bunch of stuff from the product rules, I'll just have a couple of chain rules. In fact, specifically, instead of having a quotient rule and a bunch of product rules, I'll have 1, 2, 3, 4, 5 chain rules that I need to take care of. So I'll start off by finding the natural log of both sides. So a natural log of y equals the natural log of all of this. And then I'm going to use log properties to my advantage. Whenever I divide, that's going to be a subtraction. And whenever I multiply, that's going to be an addition, giving me the natural log of x squared plus the natural log of the tangent of x plus the natural log of 4x minus 3 minus the natural log of e to the x minus the natural log of x minus 6. We can simplify a couple of these to our advantage. The natural log of x squared, I can use log properties again to get rid of exponents. 2 times natural log of x, which means I don't have to do a chain rule for that problem anymore. For the natural log of my tangent, I could split it into sine over cosine, but I don't gain enough of a benefit for doing that, so I won't this time. The natural log of e to the x, those cancel, so I just have a minus x in place of that, and then a minus natural log of x minus 6. And I'll take the derivative of this. That'll give me 1 over y prime, equals, now I'll just run through my derivatives here. I'll have 2 times 1 over x plus 1 over tangent of x times secant of x quantity squared plus 1 over 4x minus 3 times 4 from chain rule minus 1 over x minus 6 multiplied by a 1 from the chain rule, which means my y prime is equal to y times 2 over x plus secant of x squared over tangent of x plus 4 over 4x minus 3 minus 1 over x minus 6. And of course, again, since I gave you a function of x as a question, you should give me a function of x as an answer. So we'll substitute back in our y. As terrible as it sounds. Let me try to use technology again. Paste. Alright, I am such a cheater. This concludes all of our essential review materials out of 1040. Remember, all of this stuff will be on the first exam in addition to the next 4 sections.